Welcome back. We are Group 2, and this is our Brant Hall simulation. Our group consists of me, Brent Flores, Adam Hawker.
We also have Frank Fan, and then myself, Kyler Howard.
When creating our model, we chose the rooms on the floor plan that are currently used by students for living purposes. For our first trial of the third floor, our testable number of rooms started at 26, and we also chose 25 for the second floor. With our third and fourth trials, we wanted to expand more and test the differences when we added more rooms. Our third trial consisted of 29 rooms, while our fourth had 28. For consistency and good measurable data, we decided to drop the M&M from about the same height from the paper and always drop them around the center of the floor plans. Our data consisted of several different types of entries. The susceptible data refers to the number of people who have the ability to become infected. We measure the change in the number of people infected after each drop. We also included the derivative of the infected, our model slope function that we obtained from the graphs, while also entering data of the sum of the squares errors and the coefficient of determination. Our first graph of data included a statistical model of derivative versus slope for the infected population. From this data, we were able to compare this with the model component, which shows the linear relationship with the data. We were then able to compute an R-squared value of about 0.647. Our second graph was the comparison of modeled versus simulated populations of infected. This was able to demonstrate the spread of the infected against the change in time. Our final graph, the derivative of infected versus the data of infected, helps us determine if there is a relationship between the rate of change in population. From our results and using the D-field operator with the given equations, we were able to determine that the population grows proportionally to an excess in the population passed, which was diminished by nearness to the ideal of population.
This is Frank, and what I'm going to do is to talk about the part B of the project, which is about choosing a number for the parameters and also for the R-squared coefficient of determination. The method we use is pretty simple. So first of all, you try to plug a couple of numbers into here and to find out if the numbers in the data infected is close to the the numbers in the model solution infected is it like close to the numbers in the data infected? And another apparent way to show it would be to just see the graph right there. So as you can see, the two lines are very close to each other, and as you can see, the numbers in the data infected 1, and the numbers in the model solution infected 1 right there. Numbers are pretty close to each other. So that's the way we choose for the number of the parameters, and based on the number right there, the equation tells us 1.11 will be the coefficient of the x right there, and also 0.807 will be the R-squared coefficient of determination. So based on this method, we do it like the same the group 2C, group 2B, and group 2A.
For our summary, we have the selected model being x prime equals a times x minus b times x minus c, and we chose to have c equals 0 and b is n, our total population. After solving it, we got our model slope function to be x prime equals ax times n minus x, where a is just some parameter. And then we can find our model solution, which is x of t is n over 1 plus n minus 1 times e to the negative ant. Our selected model, which was model number 4, fits the data because it both starts and ends with the horizontal asymptote if c is chosen to be 0. However, the initial model of x prime a of x times x minus b starts with a large population and ends with a small one, as seen in figure 1 below. When comparing this with the collected data in figure 2, it is easy to see that the model is correct, but it is needed to be multiplied by a negative 1 to make the model slope function as shown in figure 3. Description for model 4 is the population grows proportionally to an excess and the population past x equals b diminished by nearness to the ideal population x equals c. We want our model to diminish as it gets closer to a population of x equals 0 and increase to a population of x equals n. The only difference is that we did not want the population to grow past b but before b. This was accounted for with the -1 distributed through. To solve this model, we first used the separable method. Once it has been checked that it can be separated, we integrated the equation using partial fraction decomposition. Once integrated by u substitutions, we simplified it into one natural logarithm. From there, we exponentiated both sides and turned the absolute value of the x terms into the t terms. At this point, we could check if 0 was a possible constant value in the front. 0 as a constant would make x equals 0, which would then cause x prime to be 0 as well. Both of these do satisfy a model. At this point, some algebraic simplification got us to an equation for x in terms of t. When we then plugged in our initial condition of x of 0 equaling 1, we could solve for a constant c. By plugging in our constant c in terms of a and b, we go through more steps of algebraic simplification to result in a final equation in terms of an unknown a, our total population b, which we're using n, and time. Below we have our link to our spreadsheet, and below that we have some figures. The first is figure 1 representing a d field, a slope field for our model solution. It shows a population starting at some value b and ending at 0 with horizontal asymptotes at the beginning and at the end. We just needed to flip this by a -1 factor, which shows both figure 2 and figure 3. Figure 2 is one of our collected datas, which very much resembles figure 1, but as mentioned, it needed to be flipped, which is what we did in figure 3. Table 1 is different values that we use to create each of our models for our experimental runs. Our parameter n is our total population. Parameter a is some chosen value that we try to minimize the sum of square errors, get as close of a approximation as we could. Then, looking below at figures 4, 5, 6, and 7, it shows each of our values plotted against the actual collected data. On the left graphs is a statistical model of the derivative versus the slope for infected population, using our x prime equals a of x times n minus x model slope. And the right graphs all show our actually solved models compared to our collected data. You can see some are very close, some are a little off. They all are pretty good.
The scatter plot of our data representing the population infected over time shows an asymptote-like shape starting at 0 and ending around 28. The d field for the model we chose, x prime equals ax b minus x, presented an asymptote as well, starting from 0 and ending at some value b. Our data also resulted in a determination of coefficient value of 0.6470, which is closer to 1 than 0 and therefore proves an equation of good to best fit. The d field for x prime equals ax b minus x clearly demonstrates a model that best fits our data. By examining our data and comparing to that of the class, it can be determined that our parameter values were very similar, if not the same, as the values range between 0.02 and 0.03. Parameter values did not exceed more than 0.002 past 0.03 and did not surpass more than 0.005 less than 0.02. From a general perspective, the class's parameters stayed between this range, and therefore their models resulted to be very similar as well, considering similar shapes of the graphs representing their data. Applications of this model can be used almost everywhere in terms of graphical analysis of data. An example may include an electronic device that heats up or charges where the difference between a maximum and a minimum can reach a certain threshold. Once the threshold is reached, the device may cut off or at least remain constant until the device goes below or above the threshold again. However, this model could also be used to predict the population of a state or city over time. With more time allocated to the project in the future, I believe that more trials in each run may produce more accurate results and thus providing a much cleaner representation of a D-field model.